Hello everyone, my name is Charlie Walker. I work at the Max Planck Institute for Radio Astronomy, and today I'm going to be talking to you about probing intergalactic large-scale structure using fast radio bursts with IllustrisTNG. Now, to provide some context for this talk, fast radio burst dispersion measures are comprised of multiple components, and in particular the relationship between fast radio burst redshifts and the intergalactic component of their dispersion measures, here referred to as DM cosmic, is of cosmological interest. Now, much work of this sort involves using an average DM cosmic value composed of many individual DM cosmics from many FRBs on many different sightlines. However, some DM cosmic values can dramatically deviate from this average, as indicated by the shaded grey region, which is the standard deviation from the mean on this plot on the right-hand side. Now, these deviations are due to structural variations along different sightlines, and these arise because the universe is not completely homogeneous. It has an overall large-scale structure, commonly categorized into small, dense, hot halos, filaments which link the halos together, and large, less dense, cooler void regions. And the evolution of large-scale structure with time is of interest because it's informed by and may provide insight into currently incompletely understood mechanisms, for example, AGN feedback. Therefore, individual fast radio burst sightlines are also being increasingly investigated. And one way to explore this relationship between dispersion measure, redshift, and large-scale structure is through cosmological hydrodynamic simulations, which trace the redshift evolution of the universe with time. Our aim is to use a comprehensive simulation to create a synthetic fast radio burst population for which we can completely understand all points between source and observer for many fast radio bursts. In order to do this, we chose to use IllustrisTNG-100 for its comprehensive redshift distribution, its excellent spatial resolution, and for the cell properties and galaxy properties which the simulation provides and traces through time, all of which are useful for understanding the propagation environments of our simulated fast radio bursts. And we're currently creating fast radio bursts and probing their sightlines. To create the FRBs, we're using ray tracing to build a large population out to high redshift. And for each FRB, we're recording relevant properties, for example, electron density, which allow us to trace dispersion measure evolution along the lines of sight, classify regions into different large-scale substructures, voids, halos, and filaments, and to identify any intervening galaxies along the sightlines. Examples of some of these sightlines are on the bottom left subplot of this page. The x-axis refers to the distance travelled along the line of sight by the fast radio burst. The left-hand y-axis refers to the cumulative dispersion measure along the line of sight. And the right-hand y-axis refers to the electron density at any point along the sightline. The numbers on the plots indicate unique identification numbers for any galaxy halos traversed by the fast radio burst along the sightline. And as you can see, halo regions usually correspond to jumps in electron density and spikes in dispersion measure. Our next step is to examine the statistics of our population. Our goals include investigating the evolution of dispersion measure contributions by different types of large-scale structure with redshift, investigating the statistics of halos traversed, and comparing our simulation results both to theory and to other methods of sightline reconstruction. And we also want to provide predictions to match with future observations. Over the course of the conference, we're also interested in learning how else we could combine this work with observation and theory in order to learn more about both fast radio bursts and their propagation environments. So it'd be really great if we could talk to some people about that over the course of the conference. Thanks very much for listening.